When we talk about electricity, most people picture wires, plugs, big towers, or glowing bulbs. But the real story of electricity begins in a place so small that we can't see it with our eyes. It starts inside atoms, in the restless motion of tiny charged particles. And once we understand that, electricity suddenly stops looking mysterious and starts becoming something beautifully simple. It is the movement of charge, mainly the motion of electrons doing their eternal dance through matter. Imagine every object around you made up of countless atoms, your chair, your phone, the air, even you. Each atom has a nucleus in the center, packed with positively charged protons, and orbiting around them are negatively charged electrons. Those electrons aren't nailed down firmly. In some materials they're barely hanging on. Metals like copper or aluminum have electrons that wander more freely. That freedom is what makes electricity possible. When electrons start drifting together in the same direction, we get what we call an electric current. No magic, no mystery, just organized motion of particles that were already there. The funny thing is, this motion isn't created in a power plant. A power plant doesn't manufacture electrons the way a factory makes shoes. The electrons already live in the metal wires that stretch across the landscape. What the power plant does is persuade them to move. It's like lining up millions of tiny marbles already sitting in a tube and giving a gentle push from one end. The marbles don't appear from nowhere. They just pass the push along. Electricity is that push in action. And what persuades electrons to move? That's where the idea of electric charge becomes important. Opposite charges attract, like a magnet pulling a paperclip. Similar charges repel. If you build a situation where there are more electrons in one place and fewer in another, you've built a kind of pressure, not pressure like air in a tire, but electrical pressure. We call that voltage. Voltage is simply the potential for electrons to move. When you give electrons a pathway, that potential becomes motion. This happens all around us, sometimes in dramatic ways. When clouds rub against air and dust during a storm, electrons pile up in one place and leave another place positively charged. The imbalance becomes enormous. Nature hates imbalance, so it fixes it the fastest way possible, a huge sudden rush of electrons through the air. We call it lightning. It looks wild and violent, but it's still the same simple principle. Charge moving to restore balance. The truly astonishing thing is that this same principle quietly runs your nervous system. Your brain communicates with your muscles and organs using tiny pulses of charge that travel along nerves. These signals are far gentler than lightning, but they obey the same rules. In a sense, every thought you have and every movement you make is another story of electrons shifting from one place to another. Once you start viewing electricity like this, everyday devices become less mysterious. A battery, for example, is just a clever chemical arrangement that separates charges. One side builds up excess electrons, the other side wants them badly. Connect the two sides with a wire, and electrons rush through, powering whatever sits in their path, a flashlight, a remote control, a radio. Break the path with a switch, and the electrons simply wait again. They're patient. Even the idea of static electricity, like when you shock someone after walking across a carpet, fits perfectly into this picture. Your shoes scrape electrons off the floor and onto your body. Now you carry extra charge. When you touch a doorknob, the electrons finally see an easier path to escape, and off they go in a quick spark. You didn't summon electricity from nowhere, you simply gathered and released charge. The beauty of all this lies in its consistency. From the smallest nerve signal to the largest power line, the rules do not change. That's one of the great triumphs of science, discovering that the universe runs on principles so elegant that a child with a balloon and a sweater is playing with the same forces that drive a massive city grid. Understanding this doesn't just satisfy curiosity, it gives us power in the truest sense. When engineers design circuits, they're not guessing or hoping. They're arranging paths for electrons, controlling when they move, how fast they move, and what work they do along the way. Motors spin, speakers vibrate, screens glow, not because someone commanded them, but because electrons are simply following the paths laid out for them. And maybe the most inspiring part is that none of this requires belief in something mystical. The universe already provides everything: particles, charges, forces. Our job is to notice how they behave, ask why, test our answers, and then build on what we discover. That curiosity, that refusal to be satisfied with it just works, is what turns sparks of curiosity into entire civilizations powered by electricity. So the next time you flip a switch, imagine the quiet rush of electrons responding across miles of wire, guided by human understanding, obeying laws older than the Earth itself. It's not magic, it's not hidden. It's a story of motion, order, and insight. And it reminds us that when we understand nature at its deepest levels, we can shape our world in ways that once seemed impossible. When people think of electricity, they often imagine something human-made, like a clever invention that appeared only when we built power stations and long wires stretching across fields. But electricity didn't start with us. It was here long before cities, long before tools, long before life itself. What we call modern electricity is really just our way of guiding a natural phenomenon that the universe has been using since the beginning. Look at a thunderstorm, and you're seeing one of nature's most dramatic electrical events. Inside those dark clouds, water droplets and ice crystals crash and rub against each other. Charges separate. The top of the cloud becomes one sign of charge, the bottom becomes the opposite. The imbalance grows until the air can't hold it anymore, and then, crack! Electrons rip through the sky looking for balance. We stare at it with awe, but what you're seeing is nature doing exactly what it always does, letting charge move where it wants to go. But lightning is just the showy version. Electricity is everywhere, woven quietly into the fabric of everyday processes. Deep in the earth, molten rock moves and carries charge, creating magnetic fields that help shield our planet from harmful radiation. Somewhere out in space, enormous clouds of gas collapse under gravity, and the motion of charged particles there helps form stars. On a cosmic scale, currents of charged particles flow through space like invisible rivers, shaping entire galaxies, without any power companies, without a single switch. Electricity plays one of the most fundamental roles in the universe. And then there is life, delicate, complicated, astonishing life, depending on electricity every second. Your heart doesn't simply decide to beat. A wave of electrical signals moves through heart cells in a pattern, squeezing blood in rhythm. Every thought, memory, or decision is really a dance of charged particles moving through networks of neurons. Those impulses are tiny, almost unimaginably small, but they are what make us who we are. Electricity is not only outside us, it is one of the languages our bodies speak. Even plants, which seem quiet and passive, use electrical signaling. When a leaf is damaged, electrical impulses travel through the plant to trigger defenses. Some plants snap shut. Some release chemicals. They don't do it with gears and wires. They do it with moving charges. Electricity working quietly inside cells, organizing survival. If you rub a balloon on your hair and it clings to the wall, you've just watched nature rearrange charge again. Your hair lost electrons, the balloon gained some, and now they attract each other. That's not technology. That's the same game the universe has always been playing, charges redistributing themselves toward balance. It's the same principle behind storms, behind nerve signals, behind the subtle forces that hold atoms together. The word electricity is really our name for a deep natural tendency of the world. So when we run wires through our homes, what are we really doing? We're not creating something artificial. We're building pathways that cooperate with nature instead of fighting it. We set up conditions where electrons prefer to move in a controlled direction, and we let them do what they were going to do anyway. A generator spins because magnets and charges interact. A solar cell works because light nudges electrons into motion. Every piece of technology we use is like a conversation with nature. If we arrange things like this, what will electrons do? And nature reliably answers. What's beautiful is that once you see electricity this way, the world feels richer. Birds migrating across continents use the Earth's magnetic fields, which come from electrical movements deep underground. The shimmering curtains of the northern lights appear when charged particles from the sun collide with our atmosphere. Even the crackling sound when you pull off a sweater on a dry day is electricity at work. you start to realize that we didn't discover electricity in the sense of inventing it. We simply learned to recognize it, then learned to cooperate with it. That cooperation took curiosity. It took people noticing strange sparks, tiny shocks, compass needles turning when they shouldn't, bits of paper jumping toward rubbed amber. Each observation whispered, something is happening here, something consistent, something understandable. Over time, experiments revealed the same laws shaping both the spark from a comb and the blast of a lightning bolt. The simple truth underneath all of it is that nature behaves with incredible regularity, and when we pay close attention, we can uncover patterns that let us predict and harness those behaviors. The real wonder isn't that electricity is powerful. The real wonder is that it is universal and honest. It behaves the same way inside a neuron as it does in a cloud, the same way in the smallest circuit as it does in the vast reaches of space. Our wires and machines are just invitations, carefully built, asking charge to move along routes that help us light homes, communicate across oceans, and protect lives in hospitals. When you realize electricity isn't confined to wires, that it has always been here, shaping storms, guiding life, structuring matter, and writing the rhythms of the planet, something shifts. Technology becomes less like a trick and more like a respectful collaboration. We're not forcing the universe to do our bidding. We're listening to what it already does and learning how to work alongside it. And once you see electricity as a natural part of everything, from the spark in the sky to the thought in your mind, you discover that the real power doesn't come from sockets and switches, but from understanding. If electricity is the movement of electrons, then the next question is simple: what makes them move and how much of them are actually moving? These two ideas, the push and the flow, are at the heart of every circuit, every lightning strike, every nerve signal, every glowing screen. We give them technical names, but the concepts themselves are wonderfully intuitive. The push is what we call voltage. The flow is what we call current. And once you get the difference, a whole world that once looked complicated suddenly becomes beautifully clear. Think of voltage as a kind of electrical pressure. Not pressure like you feel on your shoulder, but more like the difference in height between 2 points on a hill. Water at the top of the hill has the potential to rush downward if you give it a path. Likewise, when there's a difference in electrical charge between two places, electrons feel the urge to move. They want to slide to a lower electrical height. That desire, that potential is voltage. You can have lots of voltage without any current at all, just like you can have a tall dam holding back a lake without letting a single drop through the gates. Current, on the other hand, is what happens when you actually open the gates. It's the amount of electrons flowing per second. Big. Current means lots of electrons moving together in an organized stream. Small current means only a few are strolling along. So when people say something uses a lot of electricity, they usually mean it pulls a lot of current. It invites many electrons to march through and do work along the way. This distinction matters because it explains so many everyday experiences that otherwise seem puzzling. A static shock from a doorknob has very high voltage, thousands of volts, yet it doesn't usually hurt you beyond a quick sting. Why? Because the current involved is tiny and lasts for a fraction of a second. Meanwhile, the outlet in your wall has a much lower voltage by comparison, but it can deliver enough current to be deadly if handled recklessly. The flow is what carries the danger, and also the usefulness. Imagine a flashlight battery. It contains chemicals that separate charge inside it, creating voltage, a little pressure waiting patiently. Connect it to a simple bulb, and suddenly electrons begin drifting through the filament. As they move, they collide with atoms in the metal, causing them to vibrate faster. Faster vibration is heat, and, at a certain point, that heat becomes light. You didn't create anything mysterious. You simply allowed voltage to become current, and current to become useful work. The same principle scales up into power plants. Turbines spin, magnets turn, charges separate, and a voltage appears across gigantic generators. That voltage patiently waits until someone flips a switch miles away, and then millions upon millions of electrons begin to move in coordinated patterns through wires, into homes, into devices. The cool part is that those electrons don't sprint through the wires at lightning speed. Instead, the push propagates like a wave, like a nudge traveling through a long line of people. Each electron bumps the next one along. The choreography, not the individual speed, is what delivers power. And then there's resistance, the quiet negotiator in this story. Some materials let electrons slide easily, others make them struggle. When electrons struggle, they lose some energy as heat. That's why wires can get warm, why toasters glow, why electric stoves heat pans. Voltage provides the push, resistance shapes the pathway, and current is the result of those two forces working together. You can almost hear nature saying, "Give me a difference, give me a path, and I'll show you what happens." Once you see it this way, circuits start to feel less like complicated spaghetti diagrams and more like simple conversations. Increase the voltage, and you increase the push. Increase the resistance, and you slow the flow. Decrease the resistance, and the flow surges. Engineers spend their lives tuning this balance. They design chips that operate on delicate, tiny currents so they don't waste energy as heat. They build power lines thick enough to carry huge currents across continents. Everywhere, it's the same rulebook. This also explains why birds can sit on high-voltage wires without harm. They aren't exposed to a large difference in voltage across their bodies. Both feet are essentially at the same electrical height, so there's no reason for significant current to flow through them. But give current a path through the bird and into the ground, and everything changes. Nature isn't playing favorites, it's following its consistent logic. In your body, nerves carefully control voltage across cell membranes. When they open specific channels, that stored potential turns into a brief, controlled current along the nerve fiber. One tiny change cascades into thought, movement, sensation. Again, nothing mystical, just the push and the flow, working on a microscopic scale. And that brings us to the inspiring part. These ideas are not just technical definitions for electricians or engineers. They're windows into how the universe behaves. Voltage and current reveal that energy moves not randomly, but according to relationships that we can understand, test, and use. The same laws that light your room also guide the sparks in a storm and the whispers inside your brain. Learning them doesn't make the world less magical. It shows that the magic is real, reliable, and deeply woven into nature. So when you hear those two words, voltage and current, don't think of them as abstract symbols in a textbook. Think of them as the language electrons speak, a push, a path, a flow, repeating everywhere from the smallest circuit to the grandest structures of the cosmos. And once we learn to listen to that language, we gain the power to shape the world with knowledge instead of superstition. And that is the beginning of true control over the forces that once seemed impossible to understand. Once we understand that electricity is the movement of electrons, another natural question appears. Why does it move so easily through some things and almost not at all through others? You can hold a metal spoon and feel nothing unusual, but touch a bare copper wire carrying current, and the story is very different. Meanwhile, you can grab a plastic handle or a wooden stick and be perfectly safe. The reason isn't mysterious. It comes down to how tightly each material holds onto its electrons, and how willingly it lets them roam. In some materials, especially metals, electrons are not tied down to any single atom. Instead, they drift in a shared pool, like people walking freely through a crowded plaza. Copper, silver, aluminum. In these, electrons can move with almost casual ease. Give them the slightest push, and a river of charge flows through the material. That's what makes these metals conductors. They don't create electricity. They simply offer electrons an easy highway to travel along. Other materials behave very differently. In rubber, glass, plastic, or dry wood, electrons are held tightly in place. They cling stubbornly to their atoms like children gripping a rope. You can push as hard as you like, and only a tiny number of electrons will budge. These materials are insulators. They are not anti-electric, they just don't provide a convenient path. And because they block the motion of charge, they become our best friends when it comes to safety. Think about a simple power cord. Inside are copper wires, chosen precisely because electrons glide through them with minimal effort. Around those wires is a thick jacket of plastic or rubber. That jacket is not decoration. It says to the electrons, you may move along this route, but not here and not there. The whole system is a negotiation between allowing electrons to travel where we want and preventing them from wandering where they shouldn't. The real beauty is that this difference between conductors and insulators comes from the microscopic structure of matter itself. Metals have atoms arranged so that outer electrons form a loose shared cloud. In insulators, the electrons are locked into bonds. Nature built the rules. We simply discovered them, then began designing with them. There's a delightful simplicity in how nature enforces these rules. If you ever wondered why birds can sit on power lines, here is the answer again, in light of conductors and insulators. The wire is a conductor, yes, but the bird is not giving electricity a reason to travel through its body. There's no significant difference in electrical height across its feet, and the air around, being largely an insulator, doesn't invite much current either. If the bird touched the wire and a grounded metal pole at the same time, suddenly, the current would find a better path through the bird, and everything changes. Not because the bird offended the laws of physics, but because the path got rearranged. In laboratories and electronics, we use this contrast deliberately. We etch microscopic pathways on chips, making some regions conductive and others insulating. Electrons are guided like tiny trains on tracks, switching, pausing, and racing according to the patterns we design. The heart of modern technology is not brute force. It's the art of saying, move here, don't move there, wait until this signal arrives, and then go. Even the ground beneath our feet plays a curious dual role. Wet soil can be a fair conductor. Dry stone may act more like an insulator. That's why grounding systems exist. They give stray current an easier, safer path than your body. Not because electricity prefers Earth sentimentally, but because Earth, when properly connected, offers a vast reservoir where charges can spread out and vanish harmlessly. You can see the same principle in lightning rods. A sharp metal tower connected to the ground practically invites electrons to choose that path instead of exploding unpredictably into a building. We're not fighting the storm. We're saying, if charge must move, let it take this controlled route. The universe approves because it always follows the path of least resistance. And then there's an interesting twist. Some materials can change sides. Heat, light, or impurities can make them conduct under certain conditions and insulate under others. These are semiconductors, the foundation of computers. They sit at the edge between allowing and refusing, between path and barrier. With them, we don't just carry electricity, we choreograph it. Thinking about conductors and insulators this way removes the sense of mystery and replaces it with something far more powerful, understanding. You start recognizing that safety devices, electronics, appliances, and even nature itself operate on one consistent idea. Electricity follows available paths, and our job is to decide which paths exist. And there's something wonderfully humbling about realizing that everything we've built using electricity, power grids, smartphones, satellites, medical devices, comes from a simple insight. Some things let electrons wander freely, and others say, not here. Out of that contrast, we built an entire civilization. So when you look at a copper wire, or a plastic handle, or a tower on a hill, know that you are seeing conversation, not accident. A negotiation with nature about where charge is allowed to flow. And the more clearly we understand how to draw those invisible roads for electrons, the more wisely, safely, and creatively we can shape the world that runs on them. Because mastery begins not with force, but with learning how to guide what wants to move. If electrons simply moved around and nothing happened, electricity would be interesting but useless. The real magic, the practical magic, is what happens when moving electrons give up energy along the way. That's when electricity becomes light, heat, motion, sound, and signals carrying information. The moment current flows through something, it interacts with matter, and matter responds. That response is where all the action is. Take a simple light bulb. Inside, a thin filament resists the flow of electrons, Not enough to stop them completely, but enough to make them struggle. As they push through, they transfer energy to the atoms in the filament, shaking them violently. When atoms shake fast enough, they glow. Suddenly, electrons that started from a distant power station end up illuminating a room, letting you read a book or cook dinner. Nothing mystical, just electrons doing work and losing energy. Why is light and heat? A toaster works the same way, except we care only about the heat. Those glowing coils aren't there for decoration. They resist current, heat up, and toast bread because the energy of moving electrons gets dumped into the metal. That heat isn't made from nowhere. It is simply one form of energy transforming into another, following rules that apply everywhere in the universe. Motors are even more delightful. Instead of turning electricity into heat, they turn it into motion. When current flows through coils of wire in a magnetic field, the electrons feel a force. That force twists the coil. Attach that twist to wheels or blades and suddenly you have a fan, a washing machine, a car window rolling up, a robot arm assembling parts. You flip a switch, electrons begin to march, and somewhere a device starts to move. A stream of invisible charges becomes mechanical action you can see, hear, and feel. It's astonishing, and yet completely logical once you know what's going on inside. Then there are speakers. Current changes direction back and forth thousands of times per second. A magnet responds, a thin cone vibrates, the air wiggles, and your ears interpret those vibrations as music or words. A singer's voice becomes an electrical pattern, travels miles through wires or the air, and turns back into sound that feels immediate and alive. Electrons carrying rhythm, pitch, emotion, it's the world's most elegant delivery system. But maybe the most extraordinary trick electricity performs is communication. In a wire, electrons don't have to travel long distances individually for information to move. Instead, patterns in their motion carry meaning. Switch them on and off in sequences, and now you have digital signals. Combine enough tiny switches and you get logic, the beginnings of computing. Billions of microscopic circuits flipping faster than you can imagine create messages, images, calculations, and connections. A simple principle, charge moving, becomes video calls, navigation systems, scientific simulations, and entire libraries stored in chips no bigger than your fingertip. Think about that for a moment. A whisper of current changes inside a microchip, and your screen lights up with maps, stories, photographs, or conversations. The electrons don't know what they're doing. They simply respond to forces. We impose the structure. We decide that one pattern means yes and another means no, and suddenly we're building languages made entirely out of electrical impulses. Nature supplies the rules. We supply the meaning. What ties all of this together is a quiet law of the universe. Energy never disappears, it only changes form. Electricity isn't a special kind of miracle. It's a traveler. It arrives carrying energy, passes it on, and leaves as something else. Heat warming a room, light filling a space, movement spinning a motor, or information pulsing through circuits. Once you see that, everyday machines stop looking mysterious and start looking like beautifully arranged energy bridges. Of course, nothing is free. Each transformation has losses. Wires warm, parts vibrate, devices heat up. We work constantly to reduce waste, to design circuits that do more with less, to let electrons deliver their energy precisely where it matters, and not where it doesn't. Efficiency is really just respect for nature's accounting. Every joule must go somewhere, so we try to guide it wisely. And there's something deeply human in this process. Long before giant power grids existed, lightning flashed, auroras shimmered, nerves fired. The universe had the ingredients. What changed is that curious minds began to ask, if electrons can do that, what else can they do? Bit by bit, people learned to coax them into lamps, radios, motors, computers. Each step was an act of imagination grounded firmly in physical law. Today, a hospital monitors a heartbeat with delicate electrical sensors, while somewhere else, a spacecraft sends signals across millions of kilometers. Both depend on the same idea, moving charges, transferring energy and meaning along paths we carefully designed. It's not brute force. It's understanding applied with patience. And if there's a lesson hiding inside all these examples, it's this: electricity is not just power, it is possibility. It is the quiet engine beneath modern life, turning invisible flows into experiences, tools, miracles of medicine, arcs of knowledge, and bridges between minds. The better we understand how those flows transform, the more capable we become of shaping a world where energy works for us instead of against us. And that is where true progress begins. By now, it might seem as if electricity is this wonderfully cooperative friend. It lights our rooms, runs our machines, carries our voices, moves our cars, and keeps our world humming. And it does, when guided properly. But nature has no sense of convenience and no sympathy for mistakes. The same electrons that gently power a tiny sensor can also unleash forces strong enough to melt metal. That's not because electricity suddenly becomes angry. It simply means the paths we provide, or fail to provide, determine the outcome. If you think about everything we've discussed, the idea of safety becomes less mysterious. Voltage provides the push, current is the flow, conductors give paths, insulators block them, and energy changes forms wherever current travels. Safety is nothing more than respecting these rules instead of pretending they don't exist. When accidents happen, it's usually because someone gave electricity a path they didn't realize they had created. Take something as ordinary as a power socket. Behind that little rectangle in the wall lies a system capable of moving enormous currents if invited. The outlet sits there quietly because there is no complete path yet, but touch a live conductor while also touching something grounded, and suddenly you become the path. Not because electricity chose you, but because from nature's point of view, you offered a simpler route. Understanding this doesn't make electricity scarier, it actually makes it calmer. You see the logic, you realize the universe is consistent, and consistency is something you can work with. That's why insulation matters. That's why switches isolate circuits. That's why breakers trip when currents get too high. None of these devices are decorations. Each one is like a small guardian that says, if something goes wrong, stop the flow. A fuse blowing may be annoying, but it's really an applause-worthy event. It sacrificed itself so something far worse didn't happen. When you see these things as part of a system designed to cooperate with natural laws rather than ignore them, you start to appreciate just how elegantly safety and function go hand in hand. And consider water. Water is often a better conductor than people realize, especially when salts and minerals are dissolved in it. Place electricity and water together, and suddenly new paths appear, unpredictable, uncontrolled. That's why we stay cautious around wet environments. Not because we live in fear, but because we understand that electricity will behave exactly as it always does, whether or not we plan for it. Even static electricity teaches this lesson. A tiny spark from a sweater is harmless, but in a fuel station or an explosive environment, the same principle can ignite vapor. Tiny charges, large consequences. Again, no mystery, a path is offered, energy releases quickly, nature responds. Learning the rules isn't about memorizing lists, it's about noticing patterns and realizing they never lie. What's remarkable is that as our knowledge deepened, we didn't just protect ourselves, we actually became capable of using electricity better. Surge protectors save delicate equipment. Ground. Ding systems carry stray currents safely away. Shielded cables prevent interference so communication stays clear. Safety is not separate from progress. In many ways, it is progress. Each improvement is really a promise. We understand a little more today than we did yesterday. And there's something deeply ethical about that. Electricity gives humanity enormous power, and power always invites responsibility. When engineers design a hospital, or wire a school, or build a plane, they aren't just solving puzzles. They're making decisions that protect lives through respect for natural law. The humility to say, let's not pretend the rules are different this time, is one of the quiet strengths behind modern civilization. Yet safety isn't only for professionals. Anyone flipping a switch, plugging in a charger, or repairing a device participates in the same grand conversation. Knowing not to overload sockets, understanding why damaged cords matter, recognizing why protective covers exist. These are not boring details. They are ways of saying, I understand that this invisible force is powerful, and I will treat it with the intelligence it deserves. And here is the truly beautiful part. The more we understand electricity, the less we rely on superstition or fear. Instead of thinking, this is dangerous because it is mysterious, we think this is powerful because it obeys rules I can learn. Knowledge doesn't make electricity safer in itself, but it makes us safer stewards of it. We live at a fascinating moment in history. Renewable power, smart grids, electric vehicles, advanced electronics, all of these rely on guiding electrons more efficiently, more responsibly, and more predictably. We are building systems that not only work but fail gracefully when something goes wrong. That is civilization growing up. Not by dominating nature, but by learning to cooperate with it at deeper and deeper levels. In the end, safety and wisdom are the same idea applied to different parts of life. Electricity reminds us that extraordinary power lives in ordinary things. Flip a switch and cities glow, send a signal and continents connect. But every switch, every line, every circuit works only because people took the time to understand how charge behaves and then designed the world around that truth. And that's the real lesson. Electricity doesn't reward bravery or punish carelessness. It simply does what it has always done. Our lives get brighter, safer, and more extraordinary the moment we choose to respect its laws, learn them well, and use them with intention, because real power belongs to those who understand it. Thank you so much for watching. If this video inspired you, be sure to like, share, and subscribe to be inspired from life for more motivational content. And remember, no matter where you are in life, you have the power to change your future. See you in the next video.